Hey folks, we're continuing on with the binomial distribution, and we're going to be taking a look in this section on the mean and standard deviation of the binomial distribution. Now in the last one, we took a look at the binomial distribution, and we can actually draw a histogram for it. It's actually not a true histogram because a true histogram implies that the x-axis is continuous in nature. And as I mentioned, these bars actually have no thickness to them. They're just simply lines for the integers 0, 1, 2, 3, 4 up to 10. But it is a distribution, and so we can calculate a mean for this distribution and a median and a standard deviation. We'll just be taking a look at the mean and the standard deviation, and you'll see how that will help us when we get into the next section on normality. Of course, if you took a look at this particular one right here on the coin example, you would see that the mean is equal to the median is equal to the mode, and that's right here, which is equal to 5. When we're talking about probability distributions, the mean is called the expected value. And what we mean by that is that suppose we have 10 coins and we flip them and we count up the number of heads. And if I was to ask you, what's your best guess as to how many heads you would get, then you would say, well, with a 50-50 chance, it should turn out to be, well, half of 10, which is 5. So, and that actually is how we do it. That's how we calculate the mean. So what we're saying here is that we would expect again to get 0.5, and that's our best guess. Another way of saying this is that if we were to do this over and over and over and over again, theoretically an infinite number of times, tossing 10 coins, counting the number of heads, do it again, toss 10 coins, count the number of heads, do it again and again and again, we would find actually that the average turns out to be 5 for all of those experiments put together. Let's take a look at how that works, or more formally, using a formula called the expected value. So the expected value of a probability distribution, which is just the mean of the probability distribution, is equal to the sum of the x's times the p of x's. Now, what you should notice is that you're actually familiar with this. When we were taking a look at Unit C, where we looked at calculating a grouped mean, that's what we had. And we could rewrite this as like so. The sum of the class marks times the f over n's, the relative frequencies. And what we're saying here then is that the x's are equivalent to the class marks in a probability distribution. And remember, we said that a p of x then is just the relative frequencies over the long run. So it's the limit of the relative frequencies over the long run. So we've actually seen this formula before, and we've actually done these calculations, but we're doing this now for probability distributions. So that's what we're looking at, is this particular formula right here. Let me give you an example down here. Is, let's say we're looking at this guy down here where n is equal to 4 and p is equal to 0.3. Well, the possible values of 4, actually let's go back here to our table here. So n is equal to 4, so that would be right in here, and then p is equal to 0.3. So these are the probabilities that we would be looking at. And that corresponds to these x's here. So an x of 0 has a probability of 0.2401. And then so on all the way down here. So what I've done here then is, if you take each x times its probability and then add them together, you would end up then with the mean. So I've done that down here. And so we've got, so there's that 0, and there's that 0.2401. And then we do that for each of the numbers from the column, and we would end up with 1.2. Now, it turns out that for a binomial distribution, that's just simply equal to n times p. So mu is equal to 4 times 0.3, which is equal to 1.2. Easy peasy. That's the way the thing works. The variance and the standard deviation are found by this formula right here. And this is really similar then to this formula, which is, we've seen this before, the sum of the mean minus the means squared times the frequencies over n. And so you can see the equivalence here. Remember, f over n is equivalent to the p of x's, and then the m is equivalent to the x here. And so you end up with basically the same formula. It turns out that a computationally equivalent formula is this. So this would be the sum of the x squares times the p of x's minus mu squared. So that's an equivalent formula here for that. Let me show you how that works then. This is using the original longer formula down here. So for the n is equal to 4 and the p equal to 0.3, we would take each value, 0, minus the mean. We calculated the mean above of 1.2 squared times the probability. We got that from the probability table on page 9. And then we do that for plus 1 minus 1.2 squared times its probability, and all the way up to the last one here. And that gives us this guy, which is the variance. Well, it turns out that actually there's an easier formula for that for a binomial distribution, and it's just simply the variance is equal to n times p times 1 minus p. So 4 times 0.3 times 0.7 is 0.84. And then finally, if we took the square root of that, then we would get the standard deviation. So the square root of 0.84, whatever that turns out to be, it's something about 0.9 or something. I haven't actually calculated that, but it's easy to run that through a calculator. So let's take a look at these guys here. Calculate the mean and the standard deviation for the coins experiment. And then we're also then going to take a look at doing it for the dice experiment. So remember, in this particular case, back up here, the coins experiment, we had n is equal to 10 coins, and then p is equal to 1/2 or 0.5, and that's the probability of getting a head for any particular coin. And x takes on the values 0, 1, 2, 3, 4, all the way up to 10. Down here, we've got, let me change colors here, n is equal to 10 dice, p is equal to 1/6, and that's the probability of getting a 1 on a die. And of course, x is just like above. X takes on the values of 0, 1, 2, 3, all the way up to 10. Now, I've actually done this calculation here in Excel. So let me just go over there. And we'll take a look at this next page here. Before we do, let's actually start here then. So with the coin tossing experiment here, so this is B13, number 10, right here. Then this is what we've got. So here's our x, here's our p of x's. Those are the probabilities that we both calculated by hand, and those are the ones that we showed in the last video about how you can find that from the table. And so what you do then is you multiply each x times its p of x. So 0 times 0.001, of course, is 0, and then 1 times that, and then I've just rounded that to 3 decimal places, 2 times 0.04 is 0.08 something or other, and all the way down here. And if we sum those up, remember that the mean is equal to the sum of the x's times the p of x's, then we get 5, which is just simply equal to n times p. So that's the mean. The standard deviation is if we take each x, and let me move over to the last column here. So this column right here, x minus mu squared times each p of x. So we would be taking 0 minus 5 is minus 5 squared is 25 times this particular guy here. This isn't exactly 0.0010. It comes out to 0.024 yada yada yada. Okay, but it rounds out to that. So that's what we end up with there on that one. And so we can do that for every one of these, add them up. And so this is the variance. That variance is actually just n times p times 1 minus p, right? N is equal to 10 times p, which is 0.5, times 1 minus p, which is 0.5. 10 times 0.5 times 0.5 is 2.5. If you take the square root of that, you will get the standard deviation. Now, here's the computational formula. If we took each, let me grab a number down here in the middle somewhere. So if we took 4 and then squared it times its p of x, then we would end up with this particular number here. We sum all those up, and that would be 25.5 minus the mean squared, so minus 25 gives you your variance. And the square root of that gives you 1.5. All right, I'm going to write that down. And so let's go back here, and we're going to take a look at calculating these guys here. So let me go back to number 10 here and say that for the mean, we're going to have that's equal to the sum of the x's times the p of x's. So that's going to be 0 times, and I need to just go back to the table here for a minute so I can pull out those numbers, times 0.0010. So I'm just getting those numbers out of the table, times 1 times 0.0098, and we go all the way up to the last one, which is 10 times 0010. This is a symmetric distribution, so we're back down to 0.0010, and that just comes to 5. And then the variance will be the sum of I'm going to use the easier formula here, the computationally equivalent formula. So this one here, so that would be 0 squared times 0.0010 plus 1 squared times 0.0098 all the way up to 10 squared times 0.0010, and then subtract off the mean, which is this guy here, squared, and you'll get 2.5. And then finally, sigma will be the square root of that, which is going to be I think it was 1.58. So now let's take a look at the dice experiment. What we've got is the mean is equal to 0 times 0.1615, and I get those from the probabilities that we calculated by hand, and also you can do that by using a binomial dist function in Excel, plus 1 times 0.3230, all the way up to 10 times Well, it looks like 0, but that's to 4 decimal places. It's not impossible to get 10 ones when you roll the dice, but it's really, really small. So it's actually 0.00000 whatever. Anyways, that comes to 1.67, which actually is just simply n times p, which is 10 times 1/6. So you get the same number. The variance is equal to 0 squared times 1615 plus 1 squared times 0.3230 all the way up to 10 squared times 0.0000, and that turns out to be, minus the mean squared, 1.67 squared, and that comes to 1.389, which is just n times p times 1 minus p. So that's equal to 10 times 1/6 times 5/6. And then the square root of 1.389 is equal to 1.18. So there's your standard deviation right there. I'm going to show you that in Excel. So let's take a look at Excel here. And this is the dice rolling experiment. Just scroll up here. So what we've got here is, here's our x values, here's our p of x values. When we multiply them together, for each row, each x times its p of x, we're going to get this column here. And when we add all those up, the sum of the x times the p of x's is just the mean. So that's 1.67. The calculation that I've just done here for the variance is if you take each x and square it times its p of x and add them all up, we would get 4.167 minus the mean, 1.667 squared, and that will give us 1.389. So that's what we've got here. This actually should say x minus mean squared. And so I'm not sure what happened there. I thought I just copied it down, but that's you can just ignore that column because really it's the yellow one that you want to use here. I do want to show you one other thing here, and that is that you can have a probability distribution which is not binomial. And so the formula that we have for the expected value actually works for any discrete distribution. Let me give you an example here. Some of you are thinking about becoming accountants. And so if you work towards your CPA, then in order to get your CPA, you have to not only pass all of your courses in your business degree, but you also have to write something called a CFE, which stands for the Common Final Examination. And so that's a professional examination, and once you pass that, then you're officially a CPA. So it's looking at the September 2020, I think it's actually the 2019 CFE pass rates, because I don't think the 2020s are out yet. And so this is talking about the year of passing. And so what this is saying is that you have 3 chances of writing the CFE and passing it. And those people who started in, let's see, 19, 18, 17, so if they wrote the CFE in the first year of 2017, 77.6% of them passed, and so they got their CFE. Some of them, though, about 23% or so, 22%, didn't, and so they went on and tried it again. And so what we found there was that by the end of 2 tries, we're up to 88% of the people passed. Or what that means is the difference between them is that 10% or so, 10, 11%, passed on the second go-around. And then you do have a third go-around, and by the end of the third, almost 91% of the people who tried the CFE passed it. And so that's an additional 3% or about 2.5% or something, who it took 3 years in order to get it. Now, when you add these together here then, so 78% and 11% and 3%, you get 91%. And so 91% of the people who go in and try their CFE will get their CFE after 3 tries, most of them on their first. But there is about 10%, not 9% or so, that don't ever get it, and then they don't have a chance actually to get it. I'm not sure if you can go back and take other courses or something and retry it again. I'm not sure on that. But let's take a look then at this last column, which is of those who passed. Then, so what I'm doing is I'm going to take 0.776 and divide that by 0.907, and that means that of those who eventually get their CFE, about 86% get it in their first year, about 12% get it in their second year, and about 3% get it in their third year. So this is just a probability distribution. What year did you pass your CFE? Did it take you 1 year, 2 years, or 3 years? And here's the probabilities. And when you add them up, they come to 100%. Remember, these are the people who actually eventually got their CFE. We can calculate the average number of years that it takes to get your CFE. So x times p of x. In each case then, you're just taking the x times its p of x, and you get these numbers in yellow here. And when you add them up, this is the expected value. So what that means is that you should expect to get your CFE in the first or second year. It's probably your first year. So the mean is it takes 1.17 years. And then we can go through and we can calculate a standard deviation using the formula from before. Here's the variance of 0.2, and then take the square root of that, and you'll get the standard deviation of 0.45. So this is not a binomial distribution. A binomial distribution, remember, of course, for one thing, you always have a 0 for an x value, so it would be a 0, 1, 2, 3, but it's really what it's measuring. So if this were a binomial distribution, it would be something like, well, what's the probability that you get your CFE in the first year? And that would be a p of 0.856, this guy right here, 0.856. And then you could, say, take a random sample of 10 accountants, CPAs, and you should find that 85% of them got their CFE in their first year, that kind of thing. That's different from this kind of problem, which is saying, how many years did it take you to get your CFE? 1, 2, or 3. Okay, so the important thing to note here then is that the formula for expected value and variance is the more common one, the more generic one, are these guys right here. So this formula right here, whoops, yeah, the expected value, or the mean, and then the variance right here. But if it's a binomial problem, they reduce down to this and this. Now, you can't do that for the CFE problem because, well, you don't have an n and a p, right? You don't have the same parameters there. I guess you got an n, but you don't have the p in the same way there. So it's not a binomial problem. It's defined differently. But this formula will work for any discrete distribution, whereas this is specific for a binomial distribution. So that's where I'm going to end this particular unit here. And that will actually bring us to some problems that we're going to work through at the end here.